at InfoCloud Technologies. Cloud Native Live is a weekly show where we have different presenters sharing their knowledge and experience around cloud native technology. And today we are having Josh and Arthur, who will be talking about how we can use Kubernetes scaling capability to actually uh, respond to on-demand query requests against your data lake, and they will be demonstrating uh, how we can optimize query analytics and uh, scale out compute-only ClickHouse instance. Uh, Please keep in mind that this is a CNCF uh, uh, CNCF affiliated live stream, and we will have to follow the CNCF code of conduct. So please be respectful towards each other in the comment section. So over to Josh and Arthur.
Okay, thanks so much, Mr. So yeah, what we're here to demonstrate today is a little bit experimental, right? This is an open source project that we've just released a little less than a month ago to the public. And so we're still building this out, but we're really excited for the new capabilities that this is going to bring to ClickHouse and how this is going to enable ClickHouse to be integrated with data lakes and object storage technologies, especially Parquet for the file format and Iceberg for the catalog format. And we are a managed service provider for ClickHouse. We manage our own managed cloud entirely on Kubernetes. We also provide a lot of tools, open source tools for running ClickHouse on Kubernetes. We're the maintainers of the Altinity operator for ClickHouse, which is probably the easiest way to deploy ClickHouse on Kubernetes. And it's also what we use heavily inside our cloud. And also as part of our bring your own cloud or bring your own Kubernetes offering, which is sort of one of the templates that I'm using for the demo today is the Terraform provider, not provider, it's just a module, right? We have a Terraform module that we provide to our customers for really quickly spinning up a production-ready ClickHouse instance in their own Kubernetes environment on AWS. And that's what I've used today to create this demo. So we're sort of using that production-ready template and then adding these experimental builds on top of it. These builds are what we're calling Project Natalia for now. And it's all about being able to create these ephemeral swarm cluster nodes, right, that can be scaled up and down. Kubernetes is amazing, of course, for scaling up and down things as very quickly, so that you can respond to whatever query load you need in order to pull that data off of S3. And in some cases, we're seeing speedups of over 50x using very cheap, right, ephemeral spot nodes that can be stateless. They don't have to have any persistent storage that can get expensive and make scaling difficult. I'm joined by my colleague, Arthur, who's one of our engineers working on the Parquet integration. Arthur, would you like to introduce yourself?
Yeah, hello guys. My name is Arthur. I'm working for Altinity. I'm a software engineer here, and I'm mainly working on ClickHouse features, especially on the Natalia project, which is what Josh is here to present. And I'll be here to answer some of the more technical and engineering questions. But the main star here is Josh, and he'll be walking you through like Natalia and how we can scale ClickHouse to data lakes.
Yeah. Oh, and it looks like we're also lucky enough to be joined by Anton, who's another one of our engineers working more on the catalog and Iceberg side of things. Anton, are you able to introduce yourself? Okay, maybe we'll get Anton in later. He should be available to help answer some of the deeper questions in case I or Arthur aren't able to answer some of the questions about how the catalog and swarm clustering is working. I'd love to hear where everybody else is from and kind of what you're working on and like what interest brought you into this live stream today. If you want to go ahead and drop that in chat, I'd love to hear from the audience. This is going to be a very interactive session. I'm going to kind of walk through how I've got this set up, and we'll look at the schema from this example data set that I'm using and maybe write some queries together sort of interactively. So if there's things that you want to see, please don't hesitate to interrupt, ask questions, poke and prod. Yeah, we really want to hear from you. So to start, I'll just kind of explain the setup, right? So I'm using Terraform to set all of this up. So we can go into the Terraform. This is all publicly available, right? And you can use our Terraform module, which then allows you to really easily define a production-ready ClickHouse cluster together with an auto-scaling, with the node pools and with an autoscaler. The way that we typically recommend running ClickHouse in production, you want to have an exclusive node for each ClickHouse instance. So autoscaling is really easy in this case, right? We're just using a horizontal autoscaler. We're not using any complex, right, node packing things like Carpenter. And it's just whenever a new node is requested, we get a new node and we get an entirely, that node gets entirely filled with one ClickHouse instance. But I do want to point out here that what we're using for our demos, these are the same ones that I'll show you in my actual Terraform configuration in a moment. But I'm using M6I extra larges. So these at the most expensive pricing possible, right? Not taking advantage of any kind of discounts or spot pricing or anything like that. These are about 19 cents an hour. So if we look at this node group, right, for my swarm, this is going to cost at an absolute maximum $4 per hour for this entire cluster. So that's just something I wanted to point out. These are not expensive, beefy nodes, right? These are basically the cheapest ones we can get. Okay, so this is sort of the example that you can find on GitHub. I encourage you to definitely pull this down, try it out, and send us your feedback, right? Like, as I said, we just released this about a month ago. We're bringing it into our cloud later this month. And right now, we're really interested in hearing your feedback on how this is working for you and if it's helping you with your use cases and what we could do differently maybe to make it better suited for your use cases. So here, let's dive into my actual live code, right? I'm setting up my providers. This is pretty straightforward. I'm just using the AWS authentication in order to set up my Helm and Kubernetes providers. And I'm setting some locals, right, just to give things names. Names are important. And then we have sort of the EKS configuration, which is using this module that we provide. Go ahead and use this anytime you want a production-ready ClickHouse on EKS. Excuse me. I have it set to not actually create the ClickHouse cluster because I'm going to do that. I don't want the more production-ready builds that come out of the box with this. The resolution is too small. Oh yes, let's definitely enhance that. Okay, is that better? Hopefully that's better. Okay, so we've got. I turned off the built-in production-ready cluster, right, because I wanted to provide my own clusters using the ClickHouse installation resource that the operator uses. And then this is kind of like not quite production-ready. I've got a few things that I'm doing that you wouldn't really want to do in production. Like I'm running all of the ClickHouse Keeper instances on a single node, even though there are 3 of them. So it's not really high availability. But the point here, right, is the swarm. So that's what we're focused on. And then we can look at ClickHouse. So this is actually just a Terraform module wrapping this Helm chart, right? So I made this really simple Helm chart, which I'll make available after the live stream. And these templates are going to be pretty similar to what you see in the Antalya examples repository that I was just looking at. So we have what we're calling our vector installation, or sort of the coordinator installation. This is going to be the main ClickHouse installation that's persistent and that we actually send our queries to. So this is just a normal ClickHouse installation. Main difference is we have some configuration to allow it to find the swarm and use the swarm for object storage optimizations. And then we're also using this specific build. I'm actually using a development build that's a little bit ahead of what you might find in our examples repo, but this is also publicly available if you want to pull down the latest bleeding edge nightly build and try it out. You could. So we've got the vector cluster, and then we have the swarm cluster, which, right, similarly, we just have a little bit of extra configuration so that the swarm cluster can register itself in Keeper and the vector cluster can find it and use it. And then, right, we have our node selector saying we want extra larges for these. We want them to be a little bit beefier than the ones for the vector cluster and for Keeper. And then we've just got our tolerations to make sure that these get scheduled on the correct nodes. And you can see we're also using, right, we've got our pod anti-affinity policy to make sure that we only get one of these on each node. And the Terraform module that we're using comes with a horizontal pod autoscaler out of the box that will provision new nodes as requested by that node selector and this pod anti-affinity policy. Then we, of course, have Keeper, and we're just using ClickHouse Keeper. Pretty simple installation, no special settings required here. We're just using this really as a way for the swarm clusters to register themselves and make themselves known to the vector cluster. Okay, so with all of that, I've got then, this is sort of the outcome of all of that, if you will, is I've got my, my vector pod, right? My single instance cluster here for the vector cluster. I've got my 3 Keeper instances running on a single node. And I've got, for now, 4 swarm nodes. We're going to start off with some queries. We're not going to use those, and then we'll use these 4. And then maybe as we're going, we'll scale this up and introduce more and more swarm nodes and see how fast we can get things to go. Yeah, so that's pretty much it for what we've got going on in the Kubernetes for now. And then for the data set, right? So the data set that we're using comes from AWS. It's very nice of them to publish this data set. There's one for Ethereum. There's also one for Bitcoin, which you'll see in our examples. But for today, I'm going to be using the one for Ethereum. I will make this bigger. Ethereum. And it's just a bunch of Parquet files, right? And you can see we're using this glob pattern to say we want all of the Parquet files for all of the Ethereum transactions for the history of the Ethereum blockchain, which is pretty cool that we have this massive data set. It's a few hundred gigabytes that we can play around with. And so I'm somewhat new to working with Parquet. And one of the things we can do, right, with these Parquet files, is to inspect them and see what's the schema, what kind of data do we have available. So this is a path to one specific Parquet file that I found in that S3 bucket. And I'm just going to go ahead and download it. It's about 1 gigabyte, so it'll take just a second. My internet's not incredibly fast. Oh, my internet's a little slow today, yeah. Sorry about that. Almost there. Okay. So if we go ahead and inspect this file, we can see, right, we've got 22 columns. What is that? 1 million something rows. And then we can look at what the actual columns are, right? So we've got gas, hash, input, nonce value, block hash, right? So all of these things that we would expect to see in like a transaction log from the blockchain. So maybe some interesting ones are the from address, the to address, the value, the block timestamp. Those are probably some of the most interesting columns. And then, of course, if we keep going, we can see the schema and the types for each one of these columns. So that's how we would do this with Parquet tools. And then there's also a way to do this, to inspect this schema using ClickHouse. Arthur, can you walk me through what that query is again to inspect this using ClickHouse?
Yeah, sure. Can you pull up a ClickHouse client?
Yep. So here I'm just shelling into that that vector pod that we had in Kubernetes, and I'm using K9s. For those who are not familiar, I highly recommend it. K9s is just by far the easiest way to interact with the Kubernetes environment in the terminal, in my opinion. We do have a password on this default user. Okay, so now we're in the vector pod, and I have a ClickHouse client up, and we can go ahead and run some queries like.
Yeah.
Oh, so I did have one view that I created. We're not going to use that. We're gonna actually interact directly with the S3 table, S3 bucket as a table. Right, and so the command. What was the query to show the?
Yeah. So select and then you pass in the columns you want, but I guess you want start for now, and then from, and then S3, and you provide the file path.
Yeah. And I'm going to use the specific file path to the one specific file, correct?
Yeah.
Mm-hmm.
And perhaps you want to add the no sign and also just parquet metadata as a literal. Yeah, that should give you what ClickHouse sees as, and then you can format it better with pretty JSON each row or the one you prefer.
Yep.
But it's pretty messy. Like I don't know if there's a way to
Yeah.
visualize this in a readable way, actually.
Yeah. So we can get this out as JSON. It's a little bit hard to read when we're zoomed in this much, right? But you can see how you could dump this into a tool that's capable of reading JSON, and then you have a really easy way to examine the schema of a specific Parquet file. So that's one way that we can get the schema out. And then we can also run queries directly against this, right? So let's say we want really simply the sum of all transactions grouped by date since the beginning of this year. This might take a second. It's going to have to query over a lot of rows. We can watch the progress. Oh, it finished. Okay, 18 seconds. That's actually not as bad as I thought it would be. Yeah, so we ran that query in 18 seconds. That was with none of the optimizations from Project Antalya, right? So that's just how long that takes for ClickHouse's out-of-the-box querying to work with an S3 bucket. But if we can do more than that, we can do better, right? So we have Hive partitions here, which is a way that we can intelligently skip some of the Parquet files, and we don't have to list and read all of them from S3, which is going to help dramatically. If we use that same query should be a little bit faster. Okay, 15 seconds. So a little bit faster, but not dramatically faster. I think the caches were already primed on this node. And then we go ahead and use that swarm cluster that's deployed, right? It should be even faster. Yeah. So we went from 15 seconds to 2.5 seconds. And that was with 4 nodes deployed. I wonder if we can speed this up. So let's go up to 8. Oops. I'm using OpenTofu actually to run all of my Terraform or TF HCL, if you will. And yeah, welcome to the CNCF OpenTofu. We love you. Yes, we would like to apply that. Okay, and now if we exit out of this, we can watch those pods come up. We'll take just a minute because we do have to provision new VMs. This is the joys of working with an operator, right? You never know exactly how long things are going to take or when it will exactly start reconciling. We can watch the operator logs and see it working. It's reconciling. It's realizing it needs to create some new stateful sets. And there we go. Okay, it's starting to spin up the new swarm clusters, swarm nodes. And we're also, one of the things that's taking a moment is that we're waiting for PVCs to get provision for each one of these as well. I will note, if you're following along with the examples in our public repo, all of the PVCs are set to be deleted as soon as the pods are deleted. So do be mindful of that. If you are trying to use this for production, it's not really set up for that right now. You'd want to change these to a volume claim policy of retain to make sure that they stick around, even if you fat finger accidentally delete the ClickHouse installation or the pods or something like that. Okay, so this is just going to take a minute for those volume claims to get all attached and provisioned. Always a great time for a quick coffee break, especially if you're asking for more than 4 nodes. I have noticed, right, if I ask for 16 nodes, it's sort of the way that the autoscaler and the EKS provisioning works. You get like 4 at a time. Okay, everything is up. And now we want to go back here and we want a vector pod. And I'll make it bigger again. Okay. And so let's try that same query again that we just ran. And if you'll recall, it ran in 2.5 seconds last time. So let's see how long it takes now. It might actually be slower because we have fresh. Oh, yeah. So it's about the same amount of time. But now that those caches are primed on those swarm nodes, it might be a little faster. Yeah. So we're getting a little faster with 8 nodes now, getting it down closer to 2 seconds instead of 2.5 seconds, pretty consistently. 1.7 seconds. Arthur, can you tell us a little bit about like what's actually being cached here? Because obviously, like, it's not caching all of the Parquet files itself, right? That would be hundreds of gigabytes. What's actually going on here?
Yeah, so it depends on how you've set up this. There's the Parquet metadata cache, which I implemented a couple of months ago, and it literally caches the metadata for each Parquet files. And the metadata contains secondary indexes like min, max stats, and Bloom filters. So that might help filtering out some files that do not even need to be read at all. But there's also the file system cache, which is able to cache the contents of Parquet files.
Okay.
So
So
those are the
that's
two main
helping.
ones.
That first one's really helping, right? Because it's reducing the number of outbound S3 calls over the network, which is
Yeah, it should
really
help
helpful,
with
right?
that. Yep.
Yeah. Okay.
And there's also an in progress cache, which I'm working right now, and you have a build that has that available, but it's unstable for now, and it should reduce dramatically the number of S3 calls that we need to make in order to list the files that are present in a bucket. But yeah, those are the main caches related to Parquet.
Okay. All right. So while we're talking about this, I'm just going to quickly scale up to 16 swarms so that can get going in the background because I know it's going to take a little while, and I want to see how fast we can get this query to go.
Yeah, and one other thing I just want to add that one of the interesting things that we did was to implement some consistent hashing techniques in order for distributing the queries among the swarm nodes so that we can reuse their warm caches and reduce the impact of scaling up and scaling down.
Okay. So how does that work? Does that?
It literally means that
works?
it literally means that ClickHouse will use some consistent hashing techniques in order to try to make sure that the same node that got because when you initiate a query in a swarm, the initiator node will split out the query between multiple nodes so that each node can take care of part of that big query, like process a chunk of the files so the initiator node can merge all of them together. But what ClickHouse does is whenever it gives a set of files to a specific node, the next following queries, it tries to mimic that behavior by providing the same set of files to be processed for the same node so that that node that contains the cached Parquet files can reuse the cache. Because it was a random distribution, it'd be problematic because some nodes that haven't processed a specific chunk of files would get a new chunk, and it just wouldn't be as efficient as it could be.
Got it. Makes perfect sense. Okay, let's quickly see how we're doing on the scale up. Yep, here we go. We're getting up to 12. We'll have 16 in just a moment, and then we can go ahead and play around with some more queries. Please feel free to ask questions about how this all is working. All right, so while we're waiting for those, I'm going to run another query that we had from our examples. So this one is going to count all, oh, got mangled a little bit. This is going to count all of the the rows in the data set since the beginning of 2024. So we can see, about 60 million rows, and it took 3.5 seconds to do that count. But we can also use a new feature that Arthur just implemented. That should speed this up.
Yeah, the first.
Or was that on by default? It was already on,
it's
wasn't
not
it?
on by default, but you need to warm the cache first, because when you set to 1, you warm the cache. And now you should see the speed up.
Got it. All right, so 3.5 seconds is the time to beat. 2.9. Okay, nice.
Yeah, I was expecting faster, but it's.
Me too.
Yeah.
Okay, nightly builds are fun.
Yeah, exactly.
This was like
And
under
if you turn off the query,
this was 0.4 seconds when I did it.
Yeah.
Yeah, let's try it.
Yeah, we see a speed up, but not as much as I was expecting. But
No, it was like 10x speed up last time. Yeah. Oh well. Okay. So let's go back to that one that we were using with the swarm. And now we have a bunch more swarm nodes. So let's see if this is sped up under, we were looking at 1.7 seconds before. Warm the caches. Ooh. Okay, getting better. Still stuck around 2.2. Okay, so this is kind of the joys of this, right? Is that there are a lot of different ways that ClickHouse can be optimized in this regard in terms of how it manages the indexes and the caches and things like that. And sometimes we're hitting specific edge cases and corner cases where specific network traffic patterns or patterns in the data are leading to some unpredictable results. But we can still show that this is dramatically faster than than it was without the swarm at all. Yeah. We can try. Let's pull some more data out of this, right? So we could say some gas. We got some value. So it seems like with these cluster types and these nodes, I'm sort of hitting the edge of what's possible in terms of speed up. We're definitely seeing some cases where it's possible to get these queries significantly under a second, and that's pretty cool. Do we have any? Is there anything anyone in the audience would like to see specifically from this data set, or type of query? Any questions for Arthur about how this is working?
So we have a few questions. If Josh and Nathan can take them.
Sure.
Yeah. So the questions are like, what challenges do traditional data lake face when scaling query workloads? How does ClickHouse's compute-only node approach overcome these limitations?
Oh, great question. So data lakes are awesome, right? One of the great things about data lakes, of course, is that we now have this shared data set that can be used for a bunch of different use cases and with a bunch of different tools. But that can also lead to disparities and challenges, and a lot of these tools aren't really optimized for real time. So what we're really trying to do with Project Antalya, think of it like a data lakehouse, if you're familiar with that term, where we're kind of bringing data warehouse and structured querying to the data lake. But really what we're ultimately trying to do, and what I'm showing here today is our current progress on the read path, and what we're actively working on right now is the write path. We have a tool called ICE coming out that we can talk about a little bit more. But what we're trying to do is optimize it so that you can have a single interface for the entire data lake and a single place to go that's SQL compatible, that has the speed of a real-time data warehouse, but all of the other benefits of the cost effectiveness and vastness of a data lake, and the ability to then share that data with other tools, maybe share it with data scientists, maybe share it with machine learning models that are sort of grazing on that data, while you have ClickHouse, consuming it at high speed for these sub-second queries that could power things like alerting workflows or real-time dashboards.
Okay. We have another question. Why is Kubernetes particularly suited for dynamically scaling ClickHouse cluster? What specific capabilities does it bring to data lake analytics?
We love running our cloud on Kubernetes, right? I don't know, in terms of data lake, that there's anything specific other than that we now have, right, all of the benefits of Kubernetes, and it's sort of the ephemeral nature of these compute nodes. Like, Kubernetes has always been really, really good at scaling ephemeral workloads, especially these swarm cluster nodes. We through our operator make Kubernetes also good at managing the persistent workloads, but it's always been good at these ephemeral workloads. So just having that sort of instant ease of scalability and ability to throw more and more compute in various forms at this problem of pulling data off of the object storage and then having all of those various caches available, it's really great. There are also some challenges though, right? Like some of the things that we're doing to optimize this, right? This is not a fully optimized demo. I'm using EBS volumes. We've got faster demos working using like NVMe storage for the caches, which works great, but there's a few more extra layers when you're dealing with Kubernetes that you have to manage when you want that sort of direct access to the highest speed storage possible.
Okay. So the next question is, can you explain why combining ClickHouse with data lake technologies like Apache Iceberg and Parquet can achieve query performance or improvement of over 10x compared to typical object storage solutions?
Oh, Arthur, do you want to take this one?
Sure. Can you please just repeat the question? I'm sorry.
Yeah, sure. Can you explain why combining ClickHouse with data lake solutions like Apache Iceberg and Parquet can achieve query of performance improvement of over 10x compared to typical storage object solution?
Well, the short answer is because it's ClickHouse. But in a nutshell, is that with the especially with the project entirely is that we can scale up and down multiple stateless compute nodes with ClickHouse, which is well known for being fast, and especially in Parquet for in column oriented formats that ClickHouse can shine. And so combining like the all of the optimizations that are present in ClickHouse for vectorized data and the ability to scale up and down, uh, I think that's like the main difference. I don't know if Josh, you have something to add there.
No, I think that's a great answer. Yeah, it's really we're combining the best of object storage and, as you said, right, ClickHouse's columnar capabilities with the columnar file format, and so you really do get the best of both worlds.
Yeah, ClickHouse is notorious for being fast on, especially on merge tree, and we are taking several of the merge tree ideas or optimizations that we apply there and applying that to Apache Iceberg and Parquet, so it can work as a query engine that is very fast.
Yeah, ClickHouse is actually really quick. I once used it for like hot and cold storage or data migration and quick access. So the next question is, what kind of workload or use cases would benefit most from this Kubernetes-based approach to scaling ClickHouse on object storage?
I mean, you just mentioned one of them, right? So you said you were using ClickHouse for hot and cold storage, which is one of the awesome capabilities of ClickHouse. And right, like this is just expanding that even further so that you can now have, right, say you have all of your data flowing directly into S3, which is a great cost-effective way to deal with, high volumes of, let's say, enterprise observability data, SIEM data, right? These things where you're tracking, maybe millions of events per second, and you need to ingest that all. Object storage is a great place to persist that very cost effectively. And then you can take advantage of the high-speed caches and the high-speed local storage that's available to the more persistent ClickHouse nodes for things like materialized views that can then power things like real-time alerts, right? Like say for on a tenant by tenant basis or something like that, if you have a SaaS product.
So the next question is, what implications does this approach have for cost management and operational efficiency in managing large-scale analytics environment?
So this is 12 times cheaper, just right off the bat, right? The storage, the object storage, compared to the EBS storage, it's 4x cheaper per gigabyte. But then with the object storage, you're only storing one copy of the data, whereas with the EBS storage, if you want high availability, you're storing at least 3 copies. So we end up with just a 12 times cheaper cost per gigabyte of storage. There are trade-offs, right? You now do have to pay for data transfer fees, which if the data transfer is not optimized can add up, but that's something that we're working on, right? Arthur's very close to that, making sure that we're minimizing the amount of data that we actually have to read remotely.
Okay, so these were all the questions that we had. Does anybody in the audience wants to ask anything from our presenters?
Okay.
Okay, there is actually
silent approval. I'm going to take that as silent approval. Oh, we've got a question.
I don't think there is any question, so okay. We can end the stream. So thank you everyone for joining in, and thanks Josh and Arthur for giving us your precious time and explaining us about the capabilities of ClickHouse clusters and optimizing them. And we will see you in the next stream.